for this lab, let me go over some of the notes for the lab and what to do. So in my school, I have identified the trees in a certain area on campus before the students go out there. This is not, if you have students identify trees, it does add time, but you could do that if you wanted to as a class using something like the iNaturalist app. The trees on my campus were very hard to identify because they're not native. They're from all over the world, actually, in Southern California. So I actually created right here, this is a map of my school campus, and I drew on the map where certain trees were and what type of tree they were. And so students could go out and choose the tree they want, and then they could look on the map and see what tree that was on the map of my school. Another option is just to identify maybe 5 different trees on your campus and assign groups to a certain tree, and you already know what trees they are and you can tell them the tree. If you don't know the exact species, like for example, there's a eucalyptus tree on my campus that I really can't tell the exact species of eucalyptus it is, so I tell the kids it's eucalyptus, and we're going to kind of estimate the density of that wood that we'll get to in just a minute. I send my students out in groups of 4, and they go and they pick one of the trees that I tell them that they can, and my printer did not print this in the same order that yours, it might have appeared on the document. So the document starts like this. Mine is printed down here. So the engage is about large trees. And then students go out and they start to measure the tree. First, however, they watch this little video on how to measure the circumference of a tree. And they will find the tree, the name of the tree, and then the condition of the tree here. Now, some of my trees, especially when we go out and do this, maybe in about December, they're deciduous, so the leaves have fallen off. So I tell them, so do you remember what that tree looked like when you passed it in the spring or the fall? What was the condition of the tree with its leaves on? And then we talk about sun exposure, and this has to do with a carbon calculator that they'll use a little bit later on, and how close it is to a building and all of this stuff. And now we get to the height of the tree. So they're going to use the clinometer to measure the height of the tree, and here's some students doing that. And so first thing that the students need to do is they need to measure the height of the person looking through the clinometer. And so let's say, for example, this student was, and it's the distance to their eyeballs, actually, because it's not their full height, it's the height to their eyes, because they're looking through the clinometer from their eyes. So let's say the student might be fairly tall at 175 centimeters tall, and they're not used to measuring themselves in centimeters, so that's a little bit fun. And then they're going to measure the distance from the tree to that person. So this person's going to stay there, or they can put a rock or some sort of marker right there. And then the reason I give them 2 measuring tapes is so that they can leapfrog them. Put one down, have one person step on the end, and then bring it over, and then step on the end and bring it over. It's just an easy way for them to measure. Okay, and so that length for D here is, let's say this is some sample data from a big sycamore that we have in the middle of our school. So maybe the distance is 720 centimeters that they're measuring here. Again, this distance here. And then the height is going to be C plus D to get this full height of the tree. And so C plus D here is 895 centimeters. So this is a pretty tall tree, almost 9 meters tall. Some of the other trees on my campus are really dinky and small, and I don't actually let them choose those ones because I just don't think it's quite as interesting. And then you're going to divide by 100 to get it in meters, so we have 8.95 meters. All right, so the circumference of the tree, talk to the students about measuring the tree at breast height, which is about 4.5 feet or 137 centimeters on the uphill side of a tree. And that's just the standard measurement that foresters use. And so they're going to wrap their measuring tape around the tree. And let's say, for example, this sample tree might be 146 centimeters, which is almost the whole tape measure. I think those tape measures are about 150 centimeters, so about 1.5 meters. And then, which is one thing to notice, they're not meter lengths, they're longer than that. So make sure that the kids know they're not counting by meters. Okay, so the circumference in meters is 1.46 meters. Okay, and then it says go back to the classroom to do these parts. So the kids get a little bit confused as what to do on the next one. So I'm going to walk through that math. This part's pretty okay using the diagrams and having them read carefully. They can usually get this part okay, but you might want to check over their numbers and make sure they make sense. All right, so the formula is diameter is the circumference divided by pi. So we found out our circumference. The last measurement that we just calculated was 1.46 meters divided by pi, so 3.14. So they can use a calculator. And so this 1.46 divided by 3.14, and I'm going to round to 0.46 meters. And in our class, how do you round? It's basically 3 sig figs. So I should round to 3 sig figs here to 0.465. Okay, calculate the volume using this formula. Okay, so they're going to get a little bit confused because they're going to see this M and they'll be like, oh, that's M, but this is actually diameter, not height. So they need to go back to the front page here, and they want the height, which is 8.95. So 8.95 meters. And now they want the square of this number, which is the diameter. So here's our diameter. So 0.465 squared. And I just messed up. So let's see, clear. 0.465 squared is, I did it wrong. Let me try it again. 0.465 squared is 0.216. And then this number here is the volume of a cylinder, I believe. All right, so let's go ahead and multiply this. 8.95, sorry, my calculator here, times 0.216 times 0.7854, and I'm going to get 1.52 meters cubed. Okay, so next we're going to do the biomass of the tree. And again, some of your students can do this just fine, and some of you need to walk them through. So you might have a sample tree like I'm doing here, and then they will follow along with their tree. Okay, so here's where you need to look up the density. So it's better to sort of know your trees ahead of time, and you need to Google it, and you need to Google it in these units. So if I Google, let's say, the sycamore tree, and I don't know exactly which species of sycamore, so I'm just going to Google in sycamore. And if you don't Google the unit, so Google sycamore kilograms per cubic meter, and then it's going to actually give you the number. And when I Google it, Google tells me that 10 to the third kilograms per meter square is from about 4.4 to 0.6. That's the density. Okay, well, I don't want it in 1,000 kilograms. So if I take these and I multiply it by 1,000, it's about 400 to about 600 kilograms per meter cubed. So I'm not in this 10 to the third anymore. So I'm just going to pick the mid-range here. So I'm just going to, for this lab, choose about 500 kilograms per cubic meter is the density of a sycamore tree. And just Google it, because there's no master list of trees and their densities. They're kind of here and there depending on the forest, and there's some data out there on the internet, but it's not, again, this master list. So the best thing to do is to Google whatever tree that you're doing. And by the way, some trees are really very terrible in terms of density. We have a few palm trees on our campus, and they are terrible, and they sequester hardly any carbon. And kids who choose these trees are flabbergasted that there's hardly any carbon stored, which is one of the reasons why the city of Los Angeles is pulling out their iconic palm trees, because they don't store carbon very much. They're not native, and they drop palm fronds on cars and damage them. So they are pulling a lot of them out for native species of trees. We do have a native palm here called the California fan palm, but it's not native. It's not the ones that you think of as the iconic tall palm trees, the coconut palms, I think. Okay, so what's the mass? We have mass is density times volume. So if we know our density is 500, then we're going to take our 500 times our volume, which we learned up here was 1.52 meters cubed. So let me just write the calculation over here. So 500 kilograms per meters cubed times 1.54 meters cubed. And now those meters cubed cancel out, and we're going to end up with kilograms. So 500 times 1.52 is equal to 760 kilograms. So that's the mass of that tree. It's a pretty heavy tree. So these calculations, the students go through them, because this is really how foresters really calculate the carbon. And when we talk about carbon offsets, so a lot of times people can buy carbon offsets. So if you're a factory owner and your factory pollutes, you can buy carbon offsets in certain states. Like California, we have carbon emission cap and trade. And so polluters can buy tracts of forest. And so they do these calculations in the forest to determine how much forest is equal to the carbon that they need to sequester. And so this are the equations based on some generalizations about trees. Now there's a problem with our cap and trade laws, is that some of the polluters have polluted more heavily in our urban areas and areas that have ethnic majorities, which ends up being an environmental and social justice issue, because they're actually polluting more because they're just buying more tracts of forest in places nobody lives. So it's it's kind of a loophole that we need to solve here. Anyway, that's a side part. All right, CO2 sequestered for the tree. So we're going to take its biomass here at 760 kilograms. And now we're going to multiply it by this big long thing, and we're going to get the carbon sequestered. Now the kids don't need to memorize this or anything, but this tells them how we determine. And if you read through it, it's pretty fascinating. And so the carbon sequestered by this tree is about 1,080, and I'll round up to a whole number there. So why is it more? Well, because it's carbon dioxide sequestered, because when a tree captures carbon dioxide and sequesters it from the atmosphere, it's removing the pounds of CO2. So it takes in the carbon dioxide, and then the oxygen does not stay, but the carbon stays into the body. So the carbon's going to be less than the actual carbon dioxide that was taken in. So there's more carbon dioxide taken in, and then the carbon from that carbon dioxide stays on the tree. So that's why this number's higher than that. Okay. So now the kids are going to calculate the benefits of trees. There's a little YouTube video to watch first, and then they're going to go to this